Now we're taking a look at a shop floor work instruction. Work instructions have changed a lot over the years. Of course, the trend today is electronic shop floor work instructions, and once again, using this detailed information that came from line balancing. So I do have pictures of the parts, and I do have CAD drawing data available to me, and I can make that available to the worker on the shop floor. I can combine that with textual descriptions of the work. I can link in the videos that I took when I did the time study, okay? Reusing that information. Of course, I have the list of parts, and I have the list of tools that I entered at the line balancing stage that are now miraculously here in the work instruction, right? It's something I don't have to add later. And as you can see in this particular case, we also have hyperlinks that go to that information, so that if there is a problem with a part or a tool, an operator can quickly select that link, make a note, and the appropriate issue is logged and sent to the appropriate people for immediate resolution. So it really is a bi-directional communication. Now the key here on work instructions that I want to say is that if you're especially a dynamic organization with a lot of variability, you don't have the time to be creating shop floor work instructions for every process you make and every product that you make. That redundancy is simply not cost effective from an engineering perspective. So the focus here on process planning in lean context is, once again, associate the work instructions to the task, define which models and options that this task applies to, models and options of your product, also referred to as variants. And then the software can automatically generate a work instruction, giving nothing but a list of models, or a model and a list of options, and then the station you're at. As a result, the software now knows every activity that's assigned to that station, and it can filter those activities to only apply to that model with those specific options, therefore creating automatically a custom generated work instruction for that exact product that operator is working on, with no extra effort required by the engineering staff. That is absolutely critical in lean process engineering. So again, you can't be sitting there in front of Excel or Word or PowerPoint creating these static documents for every possible combination you come across and then expect those to be quickly updated with every process change, or to expect them to even be accurate. And of course, if they're not quickly updated and they're not accurate, then production won't move quickly and it won't move in a quality fashion. In other words, you'll produce products with errors because your instructions are off. This is also an area that you simply can't keep pace with using paper. This is something that electronic work instructions really provide. And modern work instruction tools do this deployment through Internet Explorer shop floor website. So the technology is nothing more than putting a flat screen in each station, some of which are virtual computers in a back server, or maybe even a small low-power PC located at each workstation. This is an example of how those working stations might be arranged. It's in a larger production facility where the actual 42-inch monitor is placed, hung from the ceiling. Each operator has their own monitor that they look at, and the work instructions feed the appropriate videos and pictures to that operator for the exact product they're producing, and those pictures stay up for the amount of time that that operator should be spending on that particular task. So it's helping pace the operator, it's reminding the operator of the task that needs to be performed next. In addition, if a particular task has been changed by a process engineer recently, since that operator has maybe performed the task, then that screen will flash in yellow, highlighting to that operator that they need to pay special attention to this particular step because it has changed since they last performed it. Once again, immediate information to the plant, electronically distributed without human error, and improving the quality of the product without delaying the introduction of that product to the line. This same information is sent to logistics. Remember, whenever we change the assembly line, we are now moving where those parts need to be. And that process is another one that's continuously done poorly because it's done manually with Excel spreadsheets of part lists and bills of material that aren't dynamically reconciled every day to the engineering change orders. As a result, the parts list that people use to define what parts need to be in which station are out of date. They don't get the right parts in the right place, and the first few weeks of production go pretty rough because of that exact reason. And there's just simply no reason for that today. It's a very expensive mistake to make, and it's very easy to eliminate. So by synchronizing, of course, the in-plant logistics requirements, that is what parts are needed at which station, to the engineering change order process that we just went through the line balancing technique, we immediately get an accurate list of what parts need to be at which stations. combined with a PFET database, a plan for every part database, which indicates whether that part is logistically managed through a Kanban mechanism, where we have a two-bin container system that essentially cycles back and forth for common parts like nuts and bolts and brackets, or whether that part is provided to the line in the form of a kit, where in the back room, when that build list is issued for that particular product on the assembly line, then in the back room in supermarkets, kits are made of all the parts needed to make that exact unit, and that they are delivered to those stations and labeled with respect to the unit that those kits are appropriate for. That then will provide the exact pieces that operator should be putting on the vehicle. Of course, the operator also has a list of the pieces that they should be putting on. It's another great double check that yes, indeed, the right parts are being put on the right vehicle. The nice thing about kits is that they eliminate the need to have a lot of material in the station that you don't need at this particular point in time. Really, the only material that you should constantly store in the station are those hardware items or common brackets that, once again, can be logistically managed with a Kanban system. So whether we're dealing with kits or whether we're dealing with Kanban, the point is that we can transmit that information after the line balance electronically to the barcode systems to allow the in-plant logistics system to immediately respond to those new part delivery requirements. It's an example of a barcode system with a intelligent palm PC that's on a person's wrist, very common now. The barcode scanner is actually a Velcro strip on the finger, and people can very quickly select what they're working on, what they're picking, what they're pulling to the line or from the line. Now, the one nice thing also about these barcode-driven in-plant logistics systems is that we're still using the techniques of Kanban and kitting to manage part delivery. We're not having the MRP system tell us that we need this part now. We're letting the operators, through the presence of empty containers or through the presence of a part pick list, define when they need these parts at that station. We're simply using the scanning technology as a way to track the performance of the system. And if there is a problem, such as we run out of parts in the supermarket or somebody accidentally loses a Kanban container, that the monitoring system is able to alert us to the problem before it impacts the line's performance. In other words, shutting down the line. So these Kanban tracking and e-kitting systems, called e-Kanban and e-kitting, are critical tools today in keeping that the right parts at the right place at the right time within the facility and responding once again to changes to the line brought off by process changes or engineering change orders.